this is the last class. So our agenda is revision. So we will go through week by week. If you have any question, you just ask. Our final exam is on July the 3rd, and is 7 p.m. to 9:30 p.m. Location today, I just know the location is BSB 138. Let me check. Is it 138? I think it's 138, but I want to be sure. It is 138. Yeah, 138. Okay. So the topics is you will have 3 questions. And they are from homework 07, 08, 09, and 10. Okay. So there you go. Okay, so now the floor is yours. Which homework do you want me to revise first? Anyone? Any preference? Or which homework gave you the most problem? Anyone?
10.
Hello? Which homework?
10.
10. Question
Yeah.
number?
Question number 5.
Question number 5.
5 and 6, please.
Okay, 5 and 6. So we are going to go through homework 10. Okay, so question 5. So let me look at homework. Okay. So we are given that the stress allowable is 24 KSI and shear is 15. Determine the most economical wide flange shape that could be used to support the loading. Determine the expected for the stress max, tau max, and the principal stresses. Or mean. I could not remember when they put M. Is it the mean value? Okay. And the principal stresses at the junction of flange and the web. Okay, so that's what they ask us. Okay. So now, where do you want me to start with how to draw the shear force and bending moment diagram, or you are okay with that?
I'm okay with that.
Okay, so you are okay with, so all of you are okay with the shear force and bending moment diagram. So if we were to, we know that from the shear force and bending moment diagram, I'll just get the shear force and bending moment diagram. Okay, so this is the shear force and bending moment diagram. And there are a few things that we are going to look at. So there are a few points that we can see which one will induce a higher stress. So the first point is over. We use a different color. The first point is at this point over here. Okay. So where I drew the red line, right? This point, what it has is it has V equal to 0, and it has a M which is equal to 15.19 kilo pound feet. Okay. Then there's another point we can look at, right? So the another point that we can also investigate, or we can make a judgment which is more critical, right? Over here, where my next line is V is equal to 11.25. You take the higher value, okay? I know V that's 11.25, like you take the high value. So M is equal to minus 27 times or kilopound feet. Okay. So by observation, you know that at this point, right, failure will occur. Along the beam, okay, along the beam. So if we were to draw transformation, so if this is our X and this is our Y, and this is our rotation about Z. Okay. So we know that it will fail at a certain distance that has a combination of the shear force is 11.25 kilopound and a moment of 27. So we have determined what we are going to use already. Okay, so we realize that we are going to failure will occur at Vmax, which is equal to 11.25, and Mmax, which is equal to 27 times 10 to the power 3. We have to multiply by 12 because it's all in inches. Okay, so now it's in feet times 12 is equal to 324 times 10 to the power 3 pound inch. Let me do it again. Okay. Okay, so we know that. So from here, we are going to determine, we don't know what shape of, or what is the selection of the beam to use yet. So I did attach a table. Okay, I did attach a table down here. Did I attach a table? I think I did. Yeah. So you look at the table over here, right? We have to pick one of these beam. So the most economical, the question say the most economical means the cross-sectional area has to be the smallest. Okay, because this is steel, it sells by weight. The smaller the cross-sectional area, the better it is. Okay, so now the first thing we're going to do is we are going to select. Okay, we're going to select based on maximum based on the maximum stress. Okay, so we know that what we have is our Vmax is 3 to 4 times 10 to power 3. Okay, so now we are going to calculate our what do you call our stress that we see. Okay, our stress that we see in our beam. Okay, so now we know that stress allowable is equal to 24. Before I go on, we are going to do it based on, okay, we are going to do it based on normal stress first. Okay, so one thing about this question, right, is we know that the allowable is 24 times 10 to the power 3. We know that. Okay, so this is the material we have selected already. Okay, so our bending will be based on 24 times 10 to the power 3 first. Okay, but some of you might tell me, Eugene, this is a combined loading, right? Absolutely true. This is a combined loading situation. That's why later on we have to check, did we exceed the maximum principal stress? Okay, so for now, not yet. So based on normal stress first, we know that stress allowable is equal to my over I. And then if we were to look at the beam, okay, if we were to look at the cross section of the beam, right? The beam looks like this. Okay, the beams look like this. Okay, so it is a white flange, and we're going to calculate based on maximum what? Allowable. Okay. However, we know failure will occur here. Okay. We know that failure will occur here. Right? We understand that failure will occur there. But for now, when we say failure will occur here, is when we have combined loading. Okay. For now, we just focus on normal stress, okay, which is induced by my over I. Okay. So from here, we know that. So what are the values we know? That we know that the stress allowable is equal to 24. Is equal to 24 times 10 to the power 3. And we know that the moment that we're going to take is equal to 3 to 4 times 10 to the power 3. Okay. So what we want to find is we want to find the y or the I over y ratio, which is for this case will be equal to the moment divided by stress allowable. And I think you guys have learned this in 2P before. Okay, what do I mean we have learned this in 2P before? From bending moment, we know that tau max or tau allowable is equal to my over I, right? So we are going to let S, which is equal to I over Y. So the above function where stress max or